Okay. So this entry here, Noel and Mary, this is not okay in this type of relationship, because the social security number is the thing that defines this, that gives meaning to this entry. So it can't be null. That's captured here in this table by specifying that this is not null. The last one here, because this is a foreign key, this entry is also not allowed to exist in this table because 5555 doesn't appear in the employees table. The other thing is that while oftentimes, or many times, you have a choice of, we describe this sort of, these two methods, where if you're, here we are trying to capture this manages relationship, you could have this manages be its own table, or you could also attach it to another table. Sometimes you have a choice, like in this example. But that is not the case with a weak entity. So here, I'm going to rename this the policy dependence table. So this whole thing would be captured by the employees table, and each of these get wrapped up to be this one table. The reason for that is because if you tried to have a dependence table, then there needs to be some unique identifier here. So if you have pname and age, and you tried to handle this like a regular entity, pname is not a primary key. This would not be allowed because it's a repeat of a primary key. But as you see in this table, this is an entry that should be allowed. That you could have two Johns that share the same P name because the differentiating factor is the social security number. So in this case, you must combine them into one big table like this. I think that's basically all I wanted to say about this. Oh, other than, yeah, I'll mention this Undelete Cascade, what this means. And this is also required for a weak entity. I'll repeat, a weak entity, entries in this table owe their existence to the existence of entries in another relation. So if this employee, 1111, were to leave the company and he's gone, then what do you do with these entries? By default, they would just stay there, or you could replace them with some values. But the delete on cascade says that these would also have to be deleted. So yeah, how can we express it not be null in the form of charts? Yeah, so this was just going to be my point. I'm happy with you guys drawing a chart like this if you like, but then you'll need to add some extra notes. So, for example, how to capture this type of primary key when it's concatenated like this. I think you could do something like this. Just connect them sort of with a line, make sure that they're underlined. And you can capture the foreign key part with an arrow, but on delete cascade, I don't know, you could write it here on delete cascade, and I don't know, not null, something like this. I mean, or whatever you want to do to get the point across. But yeah, these are things that aren't captured naturally when using this sort of table format. Why can't we use policy ID in the policy dependence table instead of SSN? Oh, for the homework, you're correct. You would use the policy ID, not the SSN. The SSN, because the employee relation doesn't have a relationship with the dependence relation. It's the policy that has a relationship with the dependence relation. So you would use the policy ID. In this example, I'm directly relating the employees and the dependents, which is why I'm using SSN. But it's not the way in the homework. Oh, yeah, I'm sorry. I said that the homework is going to be due today at midnight. Yeah, somebody emailed me and notified me that I didn't have that due date correct. So it should have always been today at midnight. It's still today at midnight, and yeah, if you feel like you have some extenuating circumstances or something, you can just email me. We'll also be showing. Oh, no, Musa, you don't need to do that. I was just adding these examples for illustration. You do not need to do that on the homework. Yeah, Ishika, you can do it either way you want. You can do just the SQL notation, you can do just the drawing, or you can do both. Okay. So unless there's anything else regarding this or the homework, I will continue with our discussion of relational algebra. Silence. Clarify. We can build the dependent table two ways. One with SSN and pname superkey, or a separate pname table for dependents. So for question 3 in the homework, you can do it in as little as 3 tables or as many as 4 tables. I do not believe that there's a way to do it with 5 tables or more. So an answer exists for 3 tables and also with 4 tables. The dependent table would be wrapped up with the policy relation. And I think that that is just one table you have to combine. So for this weak entity, the only way to do it is to have one table for employees and then another table for policy dependents. You cannot have, let me do a different color. So this is okay. You could not have 1, 2, 3 tables. That's not okay. Or any other iteration. If you wanted to combine these tables and have the dependence table, that's also not okay. There is unlimited submissions, yes. Can you use the access relationships diagrams? What do you mean by that?
The ones that are created, if you put in, basically you put all this into SQL and you create it, and then you create the relationships. You click the relationships tab, and it gives you this basically an ER diagram with all the arrows and stuff.
Oh, I see. Yeah. You mean in place of an ER diagram?
Yeah, I mean it technically is an ER diagram
Yeah.
because
Yeah,
I'm
I know
also submitting my SQL.
it's a different sort of format. I mean, it's a different ER diagram than the one I'm uh, teaching in this class that comes from our text. I would prefer it if you could make it the same way. Um, yeah, that is using kind of a different type of ER diagram notation. Um, yeah, so I would prefer when you make your ER diagrams that you stick to the same format that we've taught for them in this class.
Okay.
Mm-hmm. Okay, so then let's keep going with relational algebra. Um, I'll just jump straight into these examples and first start with uh, do we have to know how to do the SQL for the test? Uh, Not for the relational model part, but we will be going into SQL, like the SQL for doing queries. So I think you might as well get comfortable with it. But yeah, for this homework, it's not necessary. And for the final, if you draw a diagram for the relational model aspect of it, it's fine. But there's really no way to avoid SQL when trying to do SQL queries. And yeah, so um, that sort of relates to why we're going over this relational algebra. Um, this Once you understand and can make queries with relational algebra, it's a very easy transition to turn any of them into SQL commands. So um, we're not just doing relational algebra for fun. It's a good motivation for how to do uh, SQL commands correctly. Um, I hope you have some notes set aside, but just as a very quick reminder, um, the what I'm calling the vocabulary of relational algebra are these operations. You have a union, you have an intersection, the set difference, the cross product, the projection, and select, rename, and really that's enough. But because I'm also teaching this natural join, when we're going through these examples, I will always try to give both, but I would prefer if you tried to avoid the natural join for now. Um, okay, so these will be the things that we'll be making use of for these examples. The last class, we had these four relations: a person, frequents, eats, and serves. And really, for the relational algebra part of it, the only thing that matters is the schema, not the entries of this table. Although here I made some entries just to... I'll do it if I think it will help illustrate a point. But yeah, really the only things you need to know here are the schema names. So to find all restaurants frequented by at least one person under the age of 18, here were the two ways that we showed how to do it. Let's see here. When you look at a query like this, it's helpful to try to figure out which relations are going to be important to manipulate. So in this case, we want people because we're looking at their age. That's something that exists in the person relation. And restaurant names that are frequented by people, this comes from the frequents table. So it's going to be, and we're not asking about food that people eat or food that restaurants serve. So we don't need either of these for this particular query. Oh, I think this is helpful as well. Serve. I haven't had good luck with this. I thought that it would save time to create a table like this, but see, it shifts it. I don't know why that happens. Anyway, so by combining these two tables together, we're going to be creating sort of a mega table. And a problem with this mega table, and this is created by the cross product here. This cross product, without the renaming, would result in a relation with this type of schema. The problem is that we don't have a way to differentiate between these two columns. So this is the reason for the rename operation here, where we're going to be renaming this to name2. Then we have a select. So this will create all possible different pairings here. So John with Mary, John with Susan, John with John, Peter with Mary, Peter with Susan, Peter with John, which is just this table here. So we'll have 6 entries altogether. And in this table, first we want to choose people who are under the age of 18. So we do that with a select. The select sort of deletes rows or filters rows. And also we want the names to match. And lastly, we want to find the restaurants. So we use the projection. So this is the way to do it without the natural join. So what's happening with the natural join is that you have a select, and it's sort of combining a cross product and a rename operation, sort of behind the scenes. So here, the natural join looks at, so this is going to be between the person relation and the frequents relation. Here I'm writing the name attribute. Here, in this example, it's redundant because it's the only named attribute that they share. And this would create this table here. The select deletes a particular row, and again, we project to get the restaurant names. Okay, any questions about that before we move on?
Can you explain that one more time, please?
Which one? The whole thing?
The correct one? Yeah, the right one.
Oh, the right one. Sure,
It says drawing,
right.
or the
So,
difference between the two. Yeah.
well, so the result is the same. It's that in some ways this natural join seems like it does some magic by skipping some steps. Here, all of the steps are very explicit. So, here, let me go through this again. Oh no. Okay. So,
Oh, and also you said the left one is the right way to do it without the natural join.
correct. Yeah.
Okay.
So they're both correct. This is without the natural join. On the right is with the natural join. So this is, the natural join is this symbol here, the bow tie. Okay, so I'll try to go through this sort of step by step. Let me move this out of the way. Okay. Ooh. Oof. First, we have the cross product. This cross product. The cross product results in this table. So it takes John and matches it with Mary. That's this entry. There's the John part, there's the Mary part. It also matches John with Susan and John with John. This is the John with Susan, and then John with John. And then it also matches Peter up with each entry in the frequence table. Scroll down just a little bit here. So this is Peter from the person relation, and this is Mary from the frequence relation. Okay, so this is just all possible pairings. Now, some of these are just kind of trash. For example, this, John being paired with Mary. So there's no, I mean, these are names that don't match. But in any case, right now, this relation has a problem because we want to choose, we only want to keep those entries or those rows where these two names match. But we can't do that because the name, or these two columns have the same name. So that's what we use the rename operation for. And now this will rename this column to something different. Okay. Now we're interested in people who are under the age of 18. So this select would get rid of these rows. So this age is too big, this age is too big, this age is too big. So we have these left. But again, we want this name, Susan, being paired with John has no significant meaning. What we care about are when the names are the same. Because this is saying that John is a 16-year-old male, and John also likes to eat at McDonald's. That's the relationship that we're interested in for this question. So in addition to the select filtering by the age, we also filter out when the names are different. So here, John is not the same as Susan, and John is not the same as Mary. So this is the result of the select. And because we're interested in the restaurants and the names of the restaurants, then you do a projection of this. Oh, sorry about that. You do a projection. So the output would just be McDonald's. So that's without the natural join. With the natural join, John. Wait. Oh boy. I remember I added this before. Yeah. With the natural join, I added this just to make it more illustrative before. The result... This is the result. So it takes the person relation and the frequency relation, and it keeps only those entries where the name portion matches. So here, it's only John that appears in both of these relations. And so it cuts out all of the other entries, and it only keeps one column name. So here, doing the cross product resulted in 2 name columns, but the natural join handles that sort of behind the scenes, and it only ends up with one named attribute called name.
Okay. Why do you prefer the left side more than the right side, the one with the natural join?
Because the natural join, it's easy to it's easy to make mistakes. That's why. At least when you're initially learning. Once you have a better idea of what's happening, then I think it's okay to avoid. But because this is an introductory class, I think it's good to sort of build things from the ground up. There's also some cases and where if you're using a natural join, what you expect to happen might not happen. I'll try to come up with a succinct example of that, but for today, I'll just keep with what I've already prepared, just to save time.
Okay, thank you so much.
Sure. Okay. If there's no other questions, I'll move on. Okay. So this is another example that we went through last class. Here I'm having both of them, both answers just in 2 different colors. I should try to be more consistent, I suppose. So we have the same relations, and oh, sorry. This should be an eats, not frequents. Okay. I'll leave it. Okay. So here we want to find all the names, or the names of all females who eat either yogurt or salad or both. And this is the same OR operator that you learned in Python. It's the logical OR. So if you have truth values like this, then the OR is true if either one is true. And it generalizes to more columns, or more variables, but I won't write that here. Okay, so here, again, we want to create a relation by combining the relations that are important to this query. In this case, it's the names and genders. So we're getting that from the person relation, because we care about females and their names, and what they eat. And we get that from the eats table here. For the, let's see if I can do this or not. Okay. So we're going to be ending up with a relation that looks like this. We run into the same problem with both of the names being the same, so we have to rename one of them. Then we have a select where we only care about gender female, and we want the food to be either yogurt or salad and not something else. And we want the names to be the same. So this is without using the natural join in red. With the natural join, you'll see that the renaming goes away, the cross product turns into a bow tie, and you can get rid of one of these names here. Any questions about this one? Okay, great. So then we'll pick up where we left off the last class. So in this example, I want to find the names of all females who eat either yogurt or salad or both. And this is very related. Find the names of all females who eat both pizza and salad, not yogurt. So I will give you, 3 minutes to work on this. And if you have an answer earlier than that, you can go ahead and type it. Otherwise,
I have another.
oh, yeah.
Yeah, can you go back to the previous example?
Uh-huh.
With the gender equal female yogurt.
Mm-hmm.
So the little caret symbols, are those like part of the notation or
Oh.
syntax of the?
Sorry. Yeah.
Like, do we have to? Yeah.
So, notation, or
After it says gender equals female, and then underneath that it's just it's a caret, and then food equals yogurt, and then what is that? A V food
right.
equals salad.
So this caret means and the V, this means or.
Okay.
Yeah, sorry, that's just the
Bet.
yeah, these are the symbols for Boolean logic.
Okay. Thank you.
Yeah. Sorry, I just did it to I'm used to it and I think it makes it look a little cleaner using slightly fewer letters. Yeah, thanks for asking.
No problem.
Okay. Okay, so I'm seeing some names here. We have, minimize this. Okay. Pi name sigma gender equals female and food equals pizza and food equals salad and name 1 equals name 2 of person cross name to name 2 of eats. Okay. Is a person who eats pizza and salad one entry or two entries? Meaning example one, John, pizza and salad. It would be the second one, Eric. Yeah. Okay, good. So, this is a good natural thing to try. But there's a big problem with it, and I'll try to illustrate that. So, I'll start with the cross product. And this would result in a table that looks like this. See, it's really stupid. If one of you guys know how I can do this without inserting and deleting columns, I'd love to hear it. But, okay. And let me add in some things here. John, 16, male. Amy, 18, female. Eats. Here I'll just have John. And he eats pizza, and John also eats salad. Actually, I'll delete this one for now. This is a nice minimal example. So, stupid. Whatever, this will have two entries. John, 16, male. John, pizza. John, 16, male. John, salad. Okay. So this is just the cross product. And then we have a rename. Fine. Okay. So I forgot this was females. Okay. So here, gender equals female. Boy. So nothing gets eliminated because of that. The gender is female. Now here, food equals pizza. Fine. But the problem is with this part. How to check that food equals pizza and food equals salad. So here, food only equals one thing, either pizza or salad. The way that the select works is it looks row by row. It doesn't have a memory. So once it checks this row, its memory gets cleared and it moves on to the next row. So, and if you can imagine a very, very, very large table, it would just require far too much memory to try to hold that much information, which is why the select only looks at individual rows and moves on. So this is a nice first guess, but it's this part highlighted in green that is the big problem with this, is this you can't do. In fact, that would just eliminate everything, because here food equals pizza. That passes this part of the test, but food does not also equal salad for this entry. So that would get eliminated, and for symmetric reasons, the salad row would also get eliminated, and you would have an empty query, or an empty result of your query. Attempt 1. Are there questions about that? Does it make sense? Thank you. Yes, please. I appreciate responses if I ask the question. So okay, then I'll leave that as the attempt 1. No good. Okay, I see. Yeah, other people's answers were similar. Would you split it in 2? What is it? Yes, you would use intersection. So Jamie, I see your answer just above, and that looks right to me. So I'm going to write it out here. And so Jamie said that you still have the same pi name, sigma gender equals female, and name equals name 2, and food equals pizza. Then doing a cross product where you rename eats and do a set intersection with basically the same query, except when the food equals salad. Perfect. Great. Yes, this is correct. So this is the way to do it. You sort of filter this in 2. So this is this relation here is the same part here. Person equals person cross product with the name, or with eats, and renaming the name column in eats. But now for this first query, for this first part, only keeping the females, checking that, oh, I'm sorry, the name. checking that the names are the same, and food equals pizza. So that will eliminate this row, and the result of this outputs Amy. That set, that relation. Then, similarly, this second relation is the same thing, except for this only keeps foods that are equal to salad and outputs the name. So this also outputs Amy. And because Amy is returned as being a female who eats pizza, also she's among the set that is female and eats salad, then their intersection is just Amy. Excellent. Any questions about this before we move on to the next example? Okay, great. Find the restaurants that are frequented only by females. And I will start the 3-minute timer. Okay. Are you guys still working? Or great. All right. Well, I'll write some of these down while people are working. Oh, I see Alejandro's is the same as Eric's. Okay. See if there's a different one. Same as Toyin. Okay. Yeah, so I'm seeing of these answers, they all look the same, except for there's some choices of swapping person and frequency here. It doesn't make a difference, so I'll just say that they're the same. Tushar is something different. Yes, okay. Yeah, very good, Tushar. Set difference, just get females. Yep. That is correct. So, yeah, good job, Tushar. So first, we'll start here. This is the way that most people started to answer. What this does is that what this query here would do is it would find the restaurants that are frequented by at least one female, not only females. So I can give a concrete example if people want, or otherwise I don't know if that's enough for people. This results in by at least one female. Is that clear enough with me just stating it, or is there anybody who wants me to give something concrete? Yeah. So here, so long there's a person who is a female, and that person frequents some restaurant, then this restaurant will be returned. Yeah. And so, actually, I can keep this. So this would be a set. I don't know how to write this. Like this, I guess. So if from this set you subtract those restaurants that are also frequented by at least one male, then the result is just what this query is asking. Those frequented by only males. Male. Frequented by at least one male. Yes. So you have a set here with at least one female. And here you have those that have at least one male. And the set difference is returning this. So this first query in green, maybe I should have just stuck with the colors, but yeah, this first query in green are those with at least one female. Here in red are at least one male. So if you take the set in green and subtract the set in red, then the result is our query, this part. And so these are only females. So this is a set difference. Excellent. Very good. All right, and we will end on this example. Find the restaurants that serve at least one pizza that John eats for less than $10. I'll get the timer going. Okay. Let's try this first one. Thank you, Toyin. Pie restaurant sigma equals 2 and equals pizza and price less than 10. And eats cross row food equals food 2 of serves. Yes, this looks almost perfect. It's missing something very small. So, yes, there you go. Name equals John. So, yeah, this one was actually one of the slightly easier ones comparatively. And I think that this ends do we need to relate the frequents table at all? No need here. It doesn't necessarily have to be a restaurant that he frequents, just the restaurants that happen to serve pizza that John eats. Yeah. Great. Oh, could you explain food equals food 2 again, please? Yeah. So here, if we just do a cross product, then the schema here that I've highlighted would look like this. And so you have two columns that have the same name. And so in order to be able to say that this is both a restaurant that John eats at, and I'm sorry, this is both a restaurant that serves pizza, and pizza is a food that John likes that is under $10. There's going to be some polluted entries because of this cross product. So you need to rename one of these food entries to have a different name, the same way as with the previous named examples. Yeah. Okay. Great. So that's it for today's class. We will continue with more examples next class. I'm hoping that we can finish them. These are the quote-unquote simpler ones. There'll be some that are more complicated next time. In any case, I will try to upload these to the course website, so you'll have them at your disposal. And good luck on your homework. Thanks.
Thank you, Professor. And I have a question. So for the project, are we